Okay, so because we're in this weird asynchronous space, and this is such a complicated topic, I've decided to just make a video for all of the problems in this set so that you guys can watch it and try to understand what's going on. So in the first one, we have a Taylor series that the natural log of x is equal to this series from n equals 1 to infinity of -1 to the n plus 1, x minus 1 to the n over n. Okay, so what it asks us to do is to say, well, let f of x be the first three non-zero terms of this. So the first term of this is x minus 1, right? So if I put a 1 in all of those, I get an x minus 1. Plus, now I put 2 in all of these, so that's actually, that's going to be not plus, it's going to be minus, because that's going to be a -1. X minus 1 squared over 2, and then plus x minus 1 cubed over 3. So these are the first three non-zero terms. 1, 2, 3. Okay, so it wants to know what is the minimum of the difference between the natural log of x and this f of x, so between these two things, on the interval from 0.3 to 1.7. So I don't actually have to do Lagrange error bonding at all for this problem. I can actually just pull out my calculator and be clever. So what I'm going to do here is I'm going to put two things in y equals, right? So we're going to put in there the natural log of x, right? And then we're going to put in this guy, x minus 1, right? Minus 1/2 x minus 1, oops, way too many parentheses there, squared, right? Plus a third x minus 1 cubed. Okay, so what I'm going to do here is I'm going to get a little clever. I'm going to say this is math. Absolute value is math number 1. Right, absolute value of, so I'm going to second vars, and I just want vars, right? Y vars function y1 minus vars y vars function y2, right? And then, okay, I don't want to graph everything. I just want to graph y3 here, so I'm actually going to turn off the graph for y1 and turn off the graph for y2, and I'm going to set a window. So my window wants to go between 0.3 and 0.7, and I just did an absolute value, so my y's should always be positive, so let's have it go between maybe 0, and it's probably going to be pretty small, so let's make it 0 and 1, and let's graph. All right, so there's my curve. My maximum happens to be on the right hand side here, right? So this is going to be at 0.3, so let's go and figure out where that maximum error is. So we're going to go second trace value. I'm going to find the value for when x is 0.3, right? And that tells me that it's at 1.1446, right? So that looks like pretty close to 0.145, and I'm going to pick answer C for that one. So by just teasing out what the problem says there, I don't have to do a whole lot of work with Lagrange. So that's kind of nice. All right, let's look at number 2. Number 2, f has derivatives for all orders of real numbers, and the fourth derivative of x is e to the sine x. Okay. If the third degree Taylor polynomial for f about x equals 0, so the center of my polynomial is 0, is used to approximate on the interval from 0, 1, what is the Lagrange bound maximum error on the interval from 0, 1? Okay, so we don't know what the third degree Taylor polynomial is, but we're going to try to figure out what its difference between that and x is, right? So we want to have the maximum for this on 0, 1, okay? So from Lagrange, we know that this is bounded above by the maximum on elements from 0 to 1, right, of the fourth derivative of x, right, over 4 factorial times x, and it's going to be minus whatever x sub 1 is going to be, right, to the fourth. Okay, so the largest, and this is an absolute value, so this is all absolute valued here. All right, so the largest value that this could be, right, sorry, that's just, I'm making this more complicated than it'd be, just x to the fourth, right? So the largest possible value for the x to the fourth here is 1, right? Because this is on 0 to 1, so this is going to be 1 to the fourth, so that's just 1, okay? This is 4 factorial, that's a constant, that's not changing. And then I need to know where is the derivative its maximum on 0 to 1. So that's e to the sine x. So if I think about this, on 0, 1, sine of x is increasing, right? Because it actually increases from 0 to pi over 2. So sine of x has its max as sine 1 on that interval. On 0 to 1, e to the x is increasing, right? It actually increases from negative infinity to infinity, so that's good. So the max of e to the sine x on 0, 1 occurs at 1. So this is going to be e to the sine 1. Okay, so that's e to the sine 1. All right, so this is just 1. So I need to know what is e to the sine of 1 over 4 factorial. Right, this is calculator active problem. So I go in, then I go second quit, e to the sine of 1. Right, double check to make sure I'm in radians. I'm in radians, that's good. And the answer is 2.31977, whatever that is, right? So I go back and I look at the answers that are there, and it is not one of the answers. Why am I not that? Because I didn't divide it by 4 factorial. So I need to divide that by 4 math probability factorial, there it is, and aha, so this over 4 factorial approximately is equal to 0.096657, and now I look at my answers, that looks like B, right? That's going to give me answer B for that one. So I maxed out everything I could max out in the problem, and then said that's the greatest possible error over the interval, and I've got my answer. All right, so let's look at part C. Part 3. Let f be a function that has derivatives of all orders. So the third degree Taylor polynomial for f about x equals 0. Okay, it converges at x equals 1. Aha, so we know that the nth derivative is bounded above by n over n plus 1 on 1 to 4. Okay. So from n equals 1 to 4. So of the following, which is the smallest value of k for which the Lagrange error bound, okay, so f of 1 minus, right, f of the third degree Taylor polynomial at 1, right, should be bound by absolute value max as x is on the interval from the center, right, which is 0 to 1 of f of n of x, right, over n. So it's going to be one more, so it's got to be 4 factorial. And we are centered at 1, right? So this is going to be, or centered at 0. So this is going to be x to the 4th, right? So again, largest possible value for x to the 4th on 0 to 1 is going to be 1. So this is going to be 1 to the 4th, and this is going to be 4 factorial. But we know this guy is bounded above by this guy. So it has to be bounded above by 4 over 5, right? So let's math that a little bit. This is going to be 4/5 times 1 over 4 factorial, which I think is one of the answers. That's B. There we go. So largest possible error is 4 over 4/5 times 1 over 4 factorial. Okay, we're going to work number 4 as though it is a calculator active problem, because otherwise this thing is pretty crazy. So if you'll allow that, it asks part A to write the third degree Taylor polynomial about f for x is equal to 2, and then use it to approximate f of 1.5. So let's think about this. This would be f of 2 plus f prime of 2 times x minus 2 plus f double prime of 2 over 2 factorial times x minus 2 squared plus f triple prime of 2 over 3 factorial times x minus 2 cubed, right? So putting in the appropriate derivatives, we're going to get -3 plus 5 times x minus 2 plus 3 halves times x minus 2 squared plus -8, so that's going to be a minus, right? Minus 8 over 6 times x minus 2 cubed, right? Okay, so we throw in there some the 1.5s, so we're going to get -3 plus 5 times -1/2 plus 3 halves times, let's see, a quarter, right? Minus 4/3 times -1/8, right? Okay, so when I put 1.5 through all that, I'm going to get that. So let's just kind of math on that a little, because we're going to actually need a number here for the next part. So let's go -3 plus 5 times -1/2, right, plus 3 halves times 1/4 minus 4/3 times -1/8. Okay, so it's a decimal, this is approximately -4.9583 repeating, giving me that as a fraction it's -119 over 24. Now I realize that I've kind of cheated a little bit here by making this calculator active, but if you stop here in the problem, you actually would get full credit because you don't have to work out the arithmetic. But we're going to need this number for part B, and we'll see why that is in a second here. All right, so let's look at part B. Part B says, okay, we know that the fourth derivative for all on the interval is bound by 3, and that's the interval in question, right? Because the center's at 2, and my point of interest is at 1.5, so this thing maxes out at 3. Okay, so I have that, and then I want to bound my approximation for f of 1.5. So I know that the difference between negative 119 over 24 and the actual value of f of 1.5 is less than or equal to the absolute value of the max, as x is on 1.5 to 2, of the fourth derivative of x over 4 factorial times, and so the largest possible value here is going to be negative 1/2 to the 4th, right? Because that's the largest gap there. So I know that this has to be 3 over 4 factorial times, that's 1 over 16, right? 4th power, I think, is 16 there. So this is 3/24, okay, times 1/16, which is going to give me, all right, so this is, let's get this as a fraction, math, enter, 1 over 128. Okay, so here's what I have. I know that I'm at negative 119 over 24. This is my estimate. The largest possible error is 1 over 128. So going downward, the lowest number that I can hit is this, right? So let's take negative 119 over 24, right? And then subtract 1 over 128, which gives me negative 4.966, which is greater than negative 5. So if I start at my estimate and I take my largest possible error and go down, I cannot hit negative 5. So negative 5 is out of reach because the difference between negative 119 over 24 and negative 5 is greater than 1 over 128. Okay, so there's no way that I can get from negative 119 over 24 to negative 5 and not exceed the error bound. So that would work part B of the problem. All right, so let's look at number 5, right? Number 5 here says let the function be given by sine, so f of x is equal to sine of 5x plus pi over 4, right? So the third degree Taylor polynomial, right? So about x equals 0. So we know the sine polynomial, right? Sine of x is going to be odds. So it's x minus x cubed over 3 factorial. So that's nice. So the third degree Taylor polynomial is just sine of 5x plus pi over 4, right, is going to be 5x plus pi over 4 minus 5x plus pi over 4 cubed over 3 factorial. There it is. That's the third degree Taylor polynomial. Awesome. So that's part A. We're done. All right. So part B. Use the Lagrange error bound to show that f of 1/10. Okay. So here's what I've got. I want to show that the functional value of 1/10 is less than the other one, right? Less than 1 over 100. Okay. So what's going on here is I need to say I need to look at what is the fourth derivative, right, of f. Okay, so what is the fourth derivative of f of x? Okay, so this is going to take a little bit of work, but we can do this. Right, f of x is the sine of 5x plus pi over 4, right? So the first derivative of x is going to be, actually, let's check something here. I have to beat 1 over 100th, right? No, I have to think a little here. Sorry, let's try that again. Yeah, f of x is sine of 5x plus pi over 4, right? So f prime of x is going to be the cosine. It's going to be 5 times, right? 5 times the cosine of 5x plus pi over 4. So f double prime of x is going to be negative 25 times the sine of 5x plus 5 over, okay. The third derivative is going to be 125 times, negative 125 times the cosine of 5x plus pi over 4. And the fourth derivative is going to be 625 times the sine of 5x plus pi over 4. Okay, so let's think here. I know that this is less than or equal to 625. I can clearly bind that. Okay, so we then know that this is going to be bound by 625 over 4 factorial, right? And the largest possible value for x here is going to be started at 0. Largest possible value is going to be 1/10, right? 1/10 to the 5th. Okay, that actually should be 1/10 to the 4th. Sorry, that's not correct. All right, so this is going to be 625 over 24 times 1 over 1, 2, 3, 4. That's 10,000, right? All right, so we can play around with this thing a little bit. I can make the numerator bigger, make the denominator smaller, right? If I make the numerator bigger and I'm making the denominator smaller, I'm still bounding above, right? So this is going to be equal to 100, and that gets me 1 over 10,000, which becomes 1 over 100, which I believe I have just shown that this is less than 100th, right? Because this is clearly, actually this one doesn't have to be a less than or equal to, that's a clearly less than. So I have now bound the error below 100th. So that's it for problem 5.